All right. Oh, it's actually, could you verify? Can you hear me? Hello.
Hello, hello, good day.
Oh, perfect.
Yes, I can hear you perfectly. So it seems that we are alone in the
Yes.
room. Oh, so people are having summertime.
Yeah.
Okay. Yes. Thank you for the session. I am placed in Argentina. Actually, 6 a.m. here.
Oh,
Uh,
wow.
Yes, but this stuff, this summer school is beautiful. So,
Ah,
uh,
nice to hear.
so okay.
Yeah, so I guess so my plan was to start this session even if no one came, but now you came, so that's great. Um, I guess if you're interested in any specific problems, we can do those first. Otherwise, I'm just going to start from problem one and try to do as many as I have time for. Do you have any preferences?
No, actually, I did not try the problem still because I am returning to Spain today,
Oh,
and I am preparing uh, all things for the trip. So, but Mm, if you could take a high overview about the problems,
yeah,
you know,
sure.
of this week.
But then I think I'll just start from problem one and go down slowly. That's good for the recording too. Cool,
Okay.
cool. All right. So the first problem was this. So let's state it in plain English because it was written sort of type theoretically. But in plain English, the problem was this. So we're given two functions, f from a to b and g from b to c. And both of these functions are embeddings. Thank you. And we also have that G composed with F is an equivalence. Now, the problem asks us to show that, first of all, F is an equivalence, and also G is an equivalence. Oops. Okay. So the way to prove this is, well, so first we can note, so yeah, proof, oops, proof. So suppose FG embedding, and suppose that G composed with F is an equivalence. So we can let's just write out the diagram for these functions. So we have A, B, and C with F here and G here and G composed with F here. And we have that this bottom one is an equivalence. So now we have two problems, right? One was to show that F is an equivalence and one was to show that G is an equivalence. But let's note this. So if F is an equivalence, so if we have a squiggly line on F, well, then this commutative diagram forces G to be an equivalence too, right? So in fact, so this implies that G is an equivalence. so it's enough to show the first thing. It's enough to show,
Yes.
so enough to show f is equiv.
Yes.
Okay, perfect. Let's try to do this. So let's define its inverse. So let's do this. Oops. We define the inverse. Define the inverse of f. Let's call it psi, going from B to A, by the composition so it's going to be this composition going. We start at B and we go into C by G, and then we go from C into A by G composed with F inverse. So our assumption was that G composed with F was an equivalent, so it has an inverse.
Yes.
All right. So let's show that that these maps cancel out. So let's show that that F composed with psi is the id. Oh, well, the id on B. Okay, so let's pick some B in B. So here's a fact. By definition of psi, we have that G applied to F applied to psi of B is equal to G of B, because, well, the left hand side here is G composed with F, and then we have psi was defined by G composed with F inverse applied to G of B. So that was by definition. So the GOF and the GOF inverse cancel out. So that's why we get that this is equal to G of B. Okay, so we have a proof of this. Very good. Well, if G of F of psi of B equals G of B, we can apply, so we can apply a function here. We can apply app of G inverse, because by assumption G was an embedding, so it has an inverse. So this in fact implies that F of psi of B equals B. And that's what we wanted to show. So we're done with this direction. And for psi, sorry, what did I write up here? Oh, I made a typo, sorry. Should be composition here. Psi composed with F homotopic to the identity on A. Well, actually, this is by construction. Since psi was GOF inverse, and if we apply composed with G, that was psi, right? And if we apply this guy to F of some A, well, this guy here cancels out with this guy here. So this is in fact just A. And so we're done. So that was the proof of that one. Oops, I hope that was clear enough. So we only apply the embedding property of G here.
Yes.
And that's what gave us the proof. Okay, that was problem one.
Yes, we have automatically the second point, right? The second part.
Yes, exactly right. So the other direction is follows by the the 2 out of 3 property for equivalences. I don't know if you've talked about this. I think you have, maybe.
Yes.
Yes.
So you comment on this at the beginning.
Yes, precisely. Yeah. Yeah, I just wanted to make sure that I was familiar. Perfect. Okay, so that was problem 1. That's a nice problem. So let's do problem 2, and this has several sub problems. So the first problem says, given a type A, so A is a type, there's a fact, there's a unique map from the empty type into A. I'm going to call it just exclamation mark A. Show that it's an embedding. Okay, and the proof of this, so solution. The proof of this is really silly because, so in order to prove that it's an embedding, we need to show that given X and Y in the empty type, we have X equals Y is equivalent, well, via app exclamation mark to exclamation mark X equals exclamation mark Y. Well, here we're done, because if we say that we're given X and Y in the empty type, we can immediately apply what's it called? Empty elimination on X, and well, anything follows if you have something in the empty type, so we're done. Done. So there's nothing to prove. So that's a silly problem. Here's a less silly problem. We're going to combine all of these later to prove a nicer statement. So problem 2.2, given A and B types, show that in left from A to A plus B, and in right from B to A plus B are embeddings. Oh yeah, that was the whole problem. Sounds like I was going to continue there. No, that's the problem. Okay. Okay, so how do we do this? Well, solution. Let's do in left. So the proof for in right will be identical. Okay. So what do we need? Well, we need for every X and Y in A that X equals Y is equivalent via app of F, app of in left is equivalent to in left X in left Y. Okay. So now how do we prove this? Well, let's forget about app for a while and just focus on the types, okay? So let's recall from the lecture, that given It's a dog outside, very loud. Ah, okay. Given S and T in A plus B, we have, so these are arbitrary now and not just in left, but for arbitrary points S and T in A plus B, we have that the identity type of S and T is equivalent to this observational equality type of S and T. Okay. I hope everyone, the one person in the room remembers what this equational identity type, sorry, this observational equality was.
Yes,
So
more or less.
it was
Yes.
defined by cases.
Yes.
But these are equivalent. And okay, so in particular, we have, if we just instantiate this equivalence with in left x and in left y, we have that in left x equals in left y is equivalent to, to ek plus of in left x and in left y. Well, let's unfold the definition of ek plus in left x and in left y. Well, this was defined to be just, this is by definition just x equals y. Okay, so we have actually proved that x equals y is equivalent to in left x, yeah, x equals y is equivalent to in left x equals in left y. But we also need to prove that it was app that was the function that gave this equivalence, right? But this inverse here, if you look at how we define it in the lecture, the map here was in fact just app in left. So by this lemma here, we have that if we instantiate on in left, we get precisely what we need, because the function going from x equals y to in left x equals in left y was precisely app in left. So we're done. So there wasn't much to prove, actually. Most of the stuff was already proved in the lecture, or at least in the lecture notes. I can't remember how far she actually got. But yeah, so of course the argument would have been exactly the same for in right. There's no difference there in proof technique. Okay, it's clear enough. So let's continue to problem 2.3. So now we're given A and B again, two types. Show that in left from A to A plus B is an equivalence if and only if B is empty. I should say B is equivalent to the empty type. Okay, how do we do this? Well, so I'm kind of gonna cheat a bit and skip one direction. So let's just say that for okay, solution. For the left implication, if B equals empty, very easy to verify that in left is an equivalence. Okay, so you can just construct the map back. We'll map things in A to things in A, and things in B you don't have to map them to anything because B is empty. So you actually get this direction will be automatic if you sit down with the details. The slightly trickier direction is the other one. Okay, so suppose that in left is an equivalence. Equiv. And suppose it's, well, with some inverse, psi, let's call it psi. So psi now goes from a plus b into a. Okay. Okay, so let's suppose we're first just going to show that if we have an element of b, we get a contradiction. Okay, that's sort of the gist of the solution. Okay, so suppose we have some b of type b. Well, because in left was an equivalence with inverse psi, we have that in left of psi of b is equal to in right of b, right? Because in right of b is an element of a plus b, and so we apply just these two inverses in left and psi. Oh, sorry, there's a typo here. Oh, sorry. In left of psi of in right of b will have to be in right of b, okay? Because we assume that these two are inverses to each other. Well, let's look at what happens if we, so we said that the identity type on a plus b was equivalent to the observational identity type. So this is equivalent to the ek plus of in left psi in right b and in right b. Well, what was the definition of the observational equality type when you had the first argument in left and the second one in right? Well, this was by definition the empty type. So since we have something in here, we have a proof of this. We also get a proof of the empty type. Okay, so we have a function now. We have constructed something that says that if we have b and b, then empty. And that is precisely what is, and this is enough to show that b is the empty type. Okay.
Okay.
Good, good. So what's next? Aha, and this problem apparently had a second part. Yeah, it was the punchline. Okay, so let's do that. So problem 2.3 part 2. Conclude from problems 2.1 to 2.3 that if A and B are both contractible, then A plus B is not contractible.
Oh.
So, I mean, this is maybe kind of obvious because if A and B are contractible, they're both points. And you take the union of 2 points, you get something with 2 points, and they're not it's not contractible anymore. But let's do it the way that is intended here by the previous problems. So, so solution. Suppose A and B contractible. And suppose for contradiction that A plus B is contractible. Well, now we have a diagram like this. Did I actually use the previous properties in my proof? Let's see. We have a diagram like this. Oh yeah, no, we do use the previous properties. Okay. So because A and A plus B are both contractible, they're both equivalent to a point. And since these two guys here are equivalences, in left is an equivalence. Okay. So by the previous exercise, we get that that B is equivalent to the empty type. But well, I don't think we need to continue here actually. This is a contradiction since B was assumed
To be contractible.
yes to be contractible. Okay, cool. Good.
Yes, but a quick question,
Yeah.
maybe. Under what conditions could you maybe show an example where A plus B is contractible? Could it be contractible?
The only time A plus B, oh, I hope I'm not lying now. The only time A plus B is contractible is if A or B is the empty type.
Yes, not more cases, right?
Right. You kind of get into some constructive issues here. Wait, I'm just trying to think if my statement is constructively valid. So yes, at least classically that holds, right? Yeah, no, but that seems to be implied by this, right? And it's super careful not to make any constructivist. I don't want to upset the constructivists in the course. But yeah, no, I think this is the case constructively too. Well, yeah, kind of. Yeah, I think that's the intuition you should have at least. Well, at least if A and B are both provably non-empty, then A plus B can never be contractible. I think that's the best I can give you. Does that kind of answer your question? Yeah.
Yes, yes, it makes sense. Yes,
Yeah.
it's clear. I think that it is not difficult to prove. Once yes. Okay.
Perfect. Okay, I think this was a pretty good one. Let me see which problem I prefer to do. Ooh, it's a long one though. Well, let's start and see how far we get. Yeah, because there's one I don't want to do. Sorry, my computer is really slow. What is going on, computer? Yeah, but okay, let's do problem number 3. I think that was a nice problem. It's a bit less trivial now. So the previous problem kind of had this trivial vibe. You were just sort of hacking away on this product type, but now we're actually going to do a problem on embeddings. So let's see.
Okay.
So problem number 3. So consider the following case. So we have type A and a function from A to B. And we have an X, a type X. We have two functions like this, F and G into X. So problem 3.1 says, suppose that G is an embedding show that F is an embedding if and only if H is an embedding. Okay. So here's yeah, okay, we can draw some nice diagrams here. Should solve the problem. Okay, so for this implication, so first of all, well, we suppose that G is an embedding. That's what we do. Sorry, what is it we're supposing again? I think I have a mistake in my notes here. We're supposing that the G is an embedding. Yes. Okay, very good. So actually, this is going to be one of these cases where one diagram solves it all. So let's do this. So if suppose that F is an embedding for the left to right implication. Oops. Yeah. So we have that for any X and Y, that up F into Fx equals Fy is an equivalence. Okay. Now, so recall, so we have from this commutative diagram that we started with that, so I can write this as a little note here. Oh shit, sorry, I'm not used to this iPad. Ah, my goodness. Where did we go? What happened? Okay, so we have from the assumption that F is homotopic to G composed with H, right? That's by assumption. So in fact, the type Fx equals Fy is going to be equivalent, or well, actually equal to the type G applied to H of X equals G applied to H of Y. Okay. But well, we have another function, right? We have app of G that takes us here from Hx equals Hy. Right? And now by assumption, app of G was an equivalence because we assume that G was an embedding. So let's actually write it the other direction. App of G inverse takes us here. And let's look at the at the composite map here from x equals y to hx equals hy. We can easily prove that this is actually equal to app of h. Well, this was an equivalence. This was an equivalence, and this was an equivalence.
So
app of H is an equivalence.
so good.
So if you want to prove that this composition here is equal to app of H, you just do it
Yeah.
by path induction. So the only tricky thing, I guess, when you want to prove that this composition is equal to app of H is that this equality here is actually going to be defined by, well, you take a path in here and you map it to P composed with Q and Q inverse on this side, where Q is the proof that that f of, okay, that's right. Qx and Qy. So Qx is a proof that f of x equals g of hx. But what happens when you path induct is that this p is going to be REFL, and this x and y, they will be the same. So the middle part here will disappear because it's REFL, and then the qx inverse and qy on the right side will cancel out and give you REFL. So yeah, there's a little bit of, you have to be a bit careful when you do this, but it's easy to prove that this whole composition is app H by path induction. Okay, so we get that app H is an equivalence, but now when we have this diagram, let's just, so what was the second problem? Now we're supposed to assume that app H is an equivalence and show that app F is an equivalence. Well, okay, let's just delete this. What happens? We still have this commutative diagram. Well, obviously this implies, so app H is an equivalence and everything here is an equivalence. So we get that app F is an equivalence too. So this sort of solves both directions.
Okay. So the only thing that needs to be a little bit elaborated from is to prove that this arrow is ape of H. Okay, it's fine.
Yeah, that this is app H.
Yes.
Yeah, I can do it in detail if you want it, if you prefer.
No, I feel that it is not necessary.
Yeah, okay.
I think that I can do it by my own. Yeah, if I have a question, I could ask by Discord. But
yeah,
I feel that it's not difficult.
No, it should be relatively straightforward. Okay, cool. And now we have right. So now we have 3.2, and we have the same diagram, and it's going to be a very similar question, but you have to apply a different proof actually. So we still have this, and now we will suppose that H is an embedding. And we are to show a similar statement. Well, we're supposed to show again that F embedding if and only if G embedding. Okay, so similar problem, but different proof technique. Okay, so but I think the proof might actually be easier. So solution. So first, let's do this direction. Suppose F is an embedding. Well, we have that F is equal to G composed with H. So this implies that G composed with H is an embedding. Okay. So now we're going to consider the following. So consider what happens if we take this diagram. So we take H inverse. I'm sorry, what was my assumption again? H inverse, where did this come from? I just had to double check the problem here. Did am I supposed to assume that it's actually an equivalence? Because I've written H inverse. I don't see where that comes from. Maybe I made my life way too easy. Let me just check. Sorry about this. Gotta find the file. This is problem 3.1.2. Ah, yeah, sorry. Yeah, I thought this whole question seemed weird. Yeah, this is way too weak. Our assumption is way too weak. So we're supposed not to assume that H was an embedding, but that H was an equivalence. Thank you. Thank God. Yeah, this was weird. Equivalence. I was just too excited when I wrote it down. Perfect. Okay. Oof, my proof still holds. Okay.
You probably survive, right?
Yeah. Okay, good. Right. So H is an equivalence. We have suppose that F is an embedding. We have that G composed with H is an embedding. Perfect. We take the diagram. We apply the this diagram. So we apply H inverse, go from B to A via H inverse, and we go to X via G, and we go from A to X via G composed with H. Okay, H was an equivalence, so also an embedding. So H inverse, well, that's also an equivalence, so that's an embedding. And we have that this is an embedding. So by part 1, I guess 3.1. So by 3.1, what we just proved was that the previous part was that this forces G to be embedding. And of course, now when we have this diagram, so for the other direction, well, it's going to be the exact same thing. So let's just take this diagram again. So for the other direction, we have assumed that that G is an embedding. So suppose G embedding. Well, okay, again, we have that this is an embedding. We have that this is an embedding. So by the previous exercise again, this implies that G of H is an embedding. Well, this is equal to F. So F is an embedding. And that's it. That's a nice little exercise. But these lemmas can be really useful actually in practice. Cool. I guess I have time for one. Oh, yeah, sorry. Yeah.
No, just if H is not a equivalence, but only an embedding, this lemma, it wouldn't be true, or
right. So if you have, I think one direction would be true, but not the other. So if H is an embedding and G is an embedding, oh well, that's kind of what we just showed in the previous part, right? Then F would be an embedding because F is a composition of two embeddings. But the other direction is not true, I think. Can I come up with a counterexample? Probably not on the spot. Let me just think 1 second. H embedding. This is an embedding. Why would that imply that G is an embedding? That's a good question. Well, maybe we can try to prove it and see where we go wrong, actually. So let's suppose that H and G are both embeddings. I want to prove that F is an embedding. So let's suppose H embedding and G embedding, and want F embedding. So we want to prove that X equals Y to Fx equals Fy is an equivalence by F. Right. Now there is no obvious way. So F was equal to, well, okay, so did I mess up the order here maybe? No. F is the composition of GH. So this is equal to G composed with H of X
equals
G composed with H of X.
Y.
This was from the diagram, right?
Yes.
Yeah. And now we have, so we assume the G was an embedding. Oops. Well, yeah, okay. No, by the way, this is the first proof, right? We did.
Yeah.
Yes. I'm confused. Wait, what was the first thing that we proved actually? Okay, so yeah, it must be the no, yeah, right, because now we're back on the first in the first case. But the other case should not be possible. Wait. I'm super confused. Yeah, because this should all be fine. Okay. Well, okay, let's instead suppose that H is an embedding and F embedding. Oh, yeah, shit. Yeah, okay, this is where it breaks. Yeah. Oh, oof, thank you. So if we assume this, well, we still have the same kind of diagram. So we can go down here via app H. Oh, sorry. we get to hx equals hy.
Yes.
And we assume now that this is an equivalence and this is an equivalence. The issue now is just we have no way of mapping like this.
Yes. Yes.
But yeah, right. That's where it breaks. Okay. Good.
Hey, sorry for you.
No, it's very good question. It's actually super rare in my own research that I stumble across embeddings. It's good for me to remind myself of how they work. Okay, I guess I think I have time for one more problem, and then so I think I'm gonna skip problems 5 and 6. 6 is a nice problem, but well, it's a bit messy, so we can do. Oh, actually, this problem is quite messy too. Okay, now let's do problem 6. Let's do problem 6. Why not? It's a bit shorter, I think, at least. Okay. So I can use a fat font. Yeah, that's nice. Okay, so problem 6. We say that f a to b is path split if two things hold. So one, f has a section, and two, the map up f from x, y to, oops, maybe I should have picked the smaller font actually. F y is, no, not is, sorry, has a section for each x, y in A. Okay, so it's path split if it has a section and app has a section. Okay. Now here's a super, this is actually a really powerful lemma. So show that f is an equivalence, equiv, if and only if f is path split. Okay. Okay, so assuming that f is an equivalence, that path split looks weaker than being an equivalence, right? So one of these directions should be easy. And indeed it is. So the left to right implication. So suppose, so solution, suppose that f is an equivalence. This implies that f has a section. Okay, so we're done with the first criterion for path splitness. And the second one that was that app f has to have a section. Well, if f is an equivalence, we know that app of f is an equivalence. So also app f has a section. So that was criteria 1 and that was criteria 2. So that's it for that direction. Okay, I shouldn't write this yet. But yeah, we're done. Check.
Okay.
The second direction is the hard one. But it's not, well, it's a bit technical, but it's a good problem because it forces you to work a little bit with transports and stuff like that. So, okay. So suppose, maybe I'll change to smaller. Yeah, that's better. Suppose that f is path split. And let's call it with a, let's call it section G. Okay. So f is a function, it has a section. Okay. Now, okay, shit, I should have done problem 5 now, but by problem 5, which we didn't do. Can look it up later. By problem 5, we have that f is an embedding.
Okay, if f is pattern split, that it is an embedding.
Yeah, I think it's weaker. So if f has a section, it has an embedding. Actually,
okay.
before I lie to you, since we're recording this, I want to check. Right, if you have kind of a family of functions, so it says that they all have sections. No, wait. Yes, precisely. Yes. Okay. Whew, yeah. I think that's in the hot book somewhere. I remember. Again, rarely work with embeddings, so I don't remember the details. But yeah, if you have a function with a section, then app is embedding. Yeah. Whew,
Okay.
perfect. Okay, great. Cool. Right. So let me find my proof again. Okay. Okay, so what do we need to do in order to prove that f is an equivalence? Well, so to prove f is equivalence, we do this. We pick some b, and we need to show that the fiber of f at b is contractible. So this is one of those rare cases where you construct an equivalence by showing that the fibers are contractible. Usually you prove that it has inverses and stuff like that, but in this case, actually, this trickier definition works better. Okay, so first of all, so in order to show that something is contractible, so enough to show that fiber of FB has a point, just any point, and 2, fiber of FB is a proposition. So any 2 points are equal. That implies that it's contractible. It's slightly nicer to prove this because the point we pick, we're gonna pick is maybe not very nice to work with later. So this way of proving it is slightly nicer. It's nice to just prove that it's a proposition because you get to pick arbitrary points. Okay, so for one, well, we have a point. Fiber of FB has a point because F has a section. So remember, to construct a point in the fiber, we need to provide 2 things. We need to provide a point A in A. And for this, we just choose the section applied to B. And then we need to provide a proof that f of A is equal to B. So in this case, that would be a proof of f of G of B equals B, which we have by assumption, because G was the section of F. Okay, so we actually get a point. Cool. So now we need to show that the fiber is a proposition. So in order to prove this, well, we need to prove that any 2 points are equal. So well, let me spell it out. Well, we're given the following things. Given 2 points A and A prime in A, and we're given a proof P that f of A is equal to B, and a proof Q that f of A prime is equal to B. And we want to show that the pair A and P is equal in the fiber of f over B to A prime and Q. If we can show this, then it's a proposition. I just wanted to spell out the sort of contents a bit more. Okay.
Yes.
So let's note the following. So what do we need to do in order to show this? Well, first we need to provide a proof that A is equal to A prime. First, need some proof. What am I going to call it? Let's call it, I call it L in my notes. Okay, let's call it L. L of A equals A prime. Well, we can do this, right? We can define L by just taking P composed with Q inverse. So P was a proof that, what was it? That wait. Oh yeah, shit. Sorry. Okay, let's start again. So if we take P composed with Q inverse, that's FA equals FA prime, right? But now we have assumed that F is an embedding. So if we take up F inverse on P composed with Q inverse, then that's going to be something of type A equals A prime, right?
Yes.
Well, it's going to be, actually, it's going to be, I'm kind of skipping some details here, but you would actually need to wrap this around with some coherence paths that actually tells you that F composed with F inverse, that F inverse composed with F is equal to the identity. But let's be informal and write it like this. Okay, so we have a proof. So let's call this L. Cool. We have a first proof that A is equal to A prime. Okay, so now how do we prove that? Well, we wanted to prove that this pair, these two pairs are equal, and we have proved that the two first components are equal. So remember the identifications over sigma types. We need to prove that in order to prove that the pairs are equal, we need to prove that we can't really say that P is equal to Q because they belong to different types. But we need to prove that if we transport over this type along L, if we transport P along this type, then we get Q. That's what we need to prove. Well, actually, what one can show is that the left-hand side here, if you transport a proof along this type, this whole thing will in fact be equal to just app F of L inverse composed with P. So that's a sort of general lemma that you would have to prove. If you just find the right statement, you can prove it very easily by path induction. So now we've reduced it to proving that this is equal to Q. So, well, let's spell out what was the definition of L. Let's unfold it a little bit. Well, in fact, let's first of all let's move out the inverse here. So remember, if you take app of f to an inverted path, that's the same thing as inverting the whole path.
Mm.
So this is equal to app f of L and the whole thing inverse composed with P. Now let's unfold the definition of L. App f, and L was defined to be app f inverse of P composed with Q inverse, right? And it was this whole thing now inverse and composed with P. Okay. Well, in fact, these two guys will cancel out now, right?
Yes.
So this whole thing is just equal to P composed with Q inverse composed with P. Now, if you invert a composition, what you do is you move in the inversion and you swap the two arguments. That's also an easy lemma that I think you mentioned, maybe at least in the AGDA course. This is equal to Q inverse inverse composed with P inverse composed with P. Okay, but great. These two guys cancel, and Q inverse inverse is just Q.
Oh,
And voila, we're done.
nice problem.
So yeah, so that's it. So this is a nice problem because well, you actually have to work with identification over pair types, which is, it's kind of nasty. I hate that this transport shows up here. When you get to cubical type theory later, you'll find it'll be a nicer way of dealing with this. But yeah, this is it's a very powerful theorem too, very useful. So I think I'm gonna stop here. I'll turn off the recordings, and then if you have any questions, we can do it off the record.